Hello, very good morning to all of you. Myself, DP Mahesh, and I'm taking fluid mechanics and for the GATE 2023, and which is going to be helpful for all of you. And this is planned as per your question paper pattern of the GATE 2023. And I take this opportunity uh, to wish all the aspirants best of luck in the forthcoming GATE 2023. And in the subject fluid mechanics, and what are the topics which we are going to cover in the next 45 minutes. And we are going to discuss the basic properties of the fluid, and we also discuss the pressure and the way of measuring the pressure. We will also discuss the hydrostatics. So one after the other we are going to discuss. And basically the fluid properties, there are a number of properties that fluid possess, in which the density, specific gravity, viscosity, and vapor pressure, specific weight, specific volume are the most important properties of the fluid. And we will go in detail. What is mass density? These are the basic properties: mass density, specific gravity, weight density. Weight density can also be called by the specific weight of the fluid. There are two names: specific gravity, specific volume, viscosity, surface tension, capillarity are the important properties of the fluids. Now, coming to the definition of these basic properties of the fluid. Firstly, mass density. So, when normally we call the density of the fluid, when you say density, it is by default, it is always mass density. Then, what is mass density? Mass density is nothing but mass density of the fluid is nothing but mass of the fluid per unit volume of the fluid, which is always expressed in the unit called kg per cubic meter. The density of water, which is 1000 kg per cubic meter, water is considered to be the standard liquid, and which has a value of density or mass density of 1000 kg per cubic meter. Similarly, the weight density, and weight density of the fluid to the volume of the fluid is called weight density, also called specific weight of the fluid, which is expressed in the unit called newton per cubic meter. The weight density of water will going to be 9810 newton per cubic meter. The unit in case of a mass density is kg per cubic meter, in case of a weight density, which is 9810 newton per cubic meter for water. So you are supposed to remember these values as far as water is concerned, since water is going to be the reference liquid, or the standard liquid or the standard fluid. Then coming to the specific gravity, the most important property of the fluid is specific gravity. Specific gravity is the ratio of the densities between the two liquids. The density of the liquid by the density of water will be called as specific gravity, because both numerator and denominator are going to be the density. Thereby specific gravity becomes unitless. If the specific gravity of a liquid which is equal to 1, which is nothing but both the denominator and the numerator will have the same liquid, thereby it is the value will become 1. So when the value is 1, the liquid is water. When the value is 1, the denominator is always the weight density of water. The numerator can be any liquid, while the denominator is always water. So the water, it can be mass density of the liquid or the weight density of the liquid. So now coming to the specific volume is also nothing but the reciprocal of the mass density. In the mass density, we have the mass of the fluid to the unit volume of the fluid, whereas in specific volume, which is volume of the fluid to the mass of the fluid, and which is applicable to the gases. And coming to the other properties, viscosity is also the one of the important property of the fluid. Now let us look at the figure. So when you look at the figure, this is actually velocity variation near a solid boundary. Here we have what exactly this profile depicts. So in this profile, this is called velocity profile. I have taken two liquid surface, that is two layers inside the liquid. So this is the boundary of the liquid, and now along the y-axis, the depth of the liquid surface is taken. Along the x-axis, the flow or the velocity of each layer of the liquid is taken. Now when you observe, with the increase of the depth from the bottom, the velocity keeps on increasing. The velocity profile shows that the velocity keeps on increase. U indicates velocity, where y indicates the depth. So at one certain depth, we have taken two layers which are adjacent to each other. So there are two layers. both will have the velocity like u and u plus du. U is the velocity of one particular layer at a known depth equals to y. At a depth equals to y plus dy, there is another layer at a very small distance from the layer where the velocity is u. We have another layer which has a velocity equals to u plus du. There is a small amount of difference in the velocity between these two layers that will be equal to du. That will be equal to du. That these two layers will have a very small, a finite distance that is called dy. So then viscosity, basically it is the property of the fluid which offer resistance to the movement of one layer of the fluid or another adjacent layer of the fluid. So the tau is a symbol. Tau is actually the tau proportional to du by dy. Actually, the tau nothing but there is a kind of some amount of the stress going to be developed between the two layers. Du is nothing but the change in the velocity between the two layers. Dy also called relative velocity. Dy is nothing but there is a clearance between those two layers. And the ratio of du by dy will also be called velocity gradient. That velocity gradient is directly proportional to the stress developed between those two layers. Then the same equation can also be written as tau is equal to mu into du by dy, where mu is constant of proportionality, popularly called viscosity or also called dynamic viscosity. Now the other properties of the fluid. Kinematic viscosity. What is kinematic viscosity of the fluid? Kinematic viscosity of the fluid is defined as dynamic viscosity to the density of the fluid. Dynamic viscosity denoted as mu, whereas density is denoted as rho. Kinematic viscosity is just the ratio of the dynamic viscosity to the density of the fluid, which is expressed in the unit called Stokes. Each Stoke is nothing but cm square per second. Now coming to the various types of the fluid. The types of the fluids are going to be ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, ideal plastic fluid. Now go back to the previous slide. In the previous slide, we have an equation. You can look at this. So there is an equation called tau proportional du by dy. Any tau proportional to du by dy means velocity gradient is directly proportional to the stress, shear stress. If any fluid which obeys this relation or law, they are called Newtonian fluid. If they do not obey this law, they are called non-Newtonian fluid. Now coming back, in this case, ideal fluid. Ideal fluid, you can see this graph depicts the variation of the stress with respect to the velocity gradient du by dy. We have ideal fluid along the x-axis. We have the ideal solid along the y-axis. There are other two liquids, fluids between the x and y axis. As I said there, Newtonian fluid is one which obeys Newton's law. Newtonian fluid is one which obeys Newton's law. Which obeys Newton's law nothing but the stress developed between the layers is going to be proportional to the velocity gradient, nothing but du by dy. Non-Newtonian fluid. When you look at the curve, this is going to be straight curve, which is nothing but that is directly proportional. And when you look at this, which is not directly proportional. Non-Newtonian fluid is one where the fluid will not going to be obey the Newton's law. Ideal plastic fluid. Ideal plastic fluid, which is again directly proportional, and ideal solid and ideal fluid are ideal fluid. When I say ideal fluid, which is an imaginary fluid, they do not possess viscosity. Ideal fluid is one, it's just an imaginary fluid. For certain derivation purpose, we will assume a fluid which has no viscosity. But strictly speaking, all the fluid which are in existence, they have some amount of viscosity. Ideal fluid, which is an imaginary fluid, as all the fluids practically, they have some amount of viscosity. Now coming to some numerical problem. This is a basic problem in the field of fluid mechanics. If 10 cubic meter of mercury, which weighs 1360 kilonewton, calculate its specific weight. The four answers are given. If 10 cubic meter of mercury weighs 1360 kilonewton, calculate its specific weight, which means that 10 cubic meter is nothing but volume of the mercury is given, and that in that volume mercury weighs 1360 kilonewton. So volume and weights of the mercury are given. It is asked to calculate what is the specific gravity, specific weight of the mercury. Specific weight, nothing but weight density of the mercury. And now when you look at this specific weight, we have one formula which is specific weight will be nothing but weight to volume ratio. Specific weight is nothing but weight to volume ratio. So weight of the mercury is given as 1360 kilonewton. 1360 is actually 1360 weight to volume 1360 into 10 to the power 4. That is, volume is given as 10 cubic meter. Then you will get specific weight, which is 136 into 10 to the power Newton. So specific weight is nothing but weight to volume ratio. So mercury has a weight of 136 kilonewton. 136 into 10 to the power 4, 10 to the power 3 Newton. It is actually 1360 into 10 to the power 3. The answer is correct. Divided by the volume, which is 10 cubic meter. Finally, you will get specific weight, which is 136 into 10 to the power Newton. Now, let us come to the another example of the basic properties of fluid. Calculate the specific gravity of a fluid having a viscosity of 0.05 poise and kinematic viscosity of 0.035 Stokes. There are 4 options. Let us work out. So dynamic viscosity of the fluid, nothing but mu. It is denoted as mu. Dynamic viscosity or viscosity one and the same, and these are given in the outdated units. Poise and Stokes are outdated, and let us convert them into the present SI system. So each you can see 0.05 poise. Then when you divide this by 10, it will be gets converted to SI unit. In the SI unit, it is always expressed Newton meter per second square. Newton meter per second square. So 0.005. Then kinematic viscosity is also given 0.0. Each Stoke is nothing but 1 cm square per second. When I say Stokes, 0.035 Stokes, so each Stoke is nothing but 1 cm square per second. So when you convert cm square to a meter square, so then multiplying 10 power minus 4, finally this will be 0.035 into 10 power minus 4 because Stoke is cm square per second. So 1 cm square nothing but 10 power minus 4 meter square. Thereby it is converted to our required unit. Now by definition, kinematic viscosity will be equals to mu by rho. Mu is nothing but dynamic viscosity. Rho is nothing but density of the fluid. Then thereby rho becomes mu by nu. It is mu, nothing but dynamic viscosity. It is nu, nothing but kinematic viscosity. When these are substituted, so you will get the answer rho 1428.5 kg per cubic meter, which is the density or mass density of the fluid. When density is known of any fluid, we can able to calculate the specific gravity. So just by knowing the density, we can calculate the specific gravity of any of the liquid. So using the formula, density of the fluid by the density of the fluid. This is a standard formula in order to calculate the specific gravity of any liquid. So by definition, that G becomes 1428.5, which is the specific gravity of the present liquid, divided by the standard liquid, which is water. Thereby, the specific gravity of the liquid given becomes 1.428. Here we have the answer. The second one is actually A, B, C, D. 1428 is the correct answer. Now coming to the fluid properties. And friends, please remember, and before you analyze any problem, you are supposed to be sound in the theory background. The concept of the theory, you are supposed to be good. Then only you can able to solve some or analyze some numerical problems will become easy only when you are sound in the theory background. Now coming to the surface tension. When you look at the figure, and this is the popular surface tension phenomenon. Actually, I have taken 3 molecules. There are 3 molecules A, B, C. The 3 molecules, and it is known that all the molecules they possess some amount of force of attraction by the surrounding molecules. Here 3 molecules are taken. The molecule A, which is completely inside the liquid. The molecule B, which is near the free surface or almost at the free surface. The C is at the free surface. Or the 3 molecules are taken. And what exactly the figure depicts is, and this arrow indicates that there are force of attraction by there is n number of molecules will surround each molecule. So thereby the molecule A will be attracted in all the direction by the surrounding molecules of the liquid. Thereby it is going to experience a resultant zero resultant, because they in all the direction when you resolve the forces, they become zero. Thereby the molecule A is in held in position, which is nothing but it is at rest or in equilibrium, means it is not going to experience any result. there it is kept in equilibrium. Similarly, the molecule B, because most of it is inside, but still it's not completely inside. So it is at the free surface. Thereby, the force of attraction by the surrounding molecules are not going to balance. And hence, it will have a downward resultant. It's going to experience a downward resultant. Similarly, the molecule C is. Both molecule B and C, as they are at the free surfaces, they're experiencing some downward resultant. And there, because of these two are experiencing the downward resultant, there will be a force at the free surface, so which will going to act in the other direction. Means, in order to keep the molecules which are at the free surface in the same position, will be a force at the free surface, that is a tensile force at the free surface, which is going to act on the molecules which are at the free surfaces. That force is called surface tension. Surface tension, by definition, which is a tensile force per unit length of the free water surface. Friends, now coming to the examples. When you look at the figure, here I have taken a liquid droplet. Normally, liquid droplet which looks in the form of a sphere, which looks in the form of a sphere like a ball. So when you let us take the half of that. When you carefully observe this edge will act as a free surface. This edge will act as a free surface. Free surface will always under the action of a tensile force, that is called surface tension. So this arrow indicating a tensile force due to surface tension. And the tensile force due to surface tension magnitude depends on what is the length of the free surface. That is most important. Now the other figure is, in this, there is a, you can observe carefully, there is a pressure force. There is a pressure force. Inside you have an area in the form of a circle, and that area there will be a pressure forces. That pressure forces, this is a tensile force. Both are equal and opposite. Both are equal and opposite. For equilibrium, these two are equal and opposite. By equating those two forces, we can get this final equation. This is actually what exactly this equation is. While solving the numerical problem, we use this equation, that is the pressure inside the droplet in excess outside. P equals to 4 sigma by D. What exactly this equation meaning is? Sigma is nothing but surface tension. That surface tension, which is a constant number for a given liquid. For a given liquid, it is expressed always in terms of so many Newton per meter length of the free water surface, where D is the size of the diameter of the droplet. Where what is that P? P is the pressure inside the droplet in excess outside pressure, which is nothing but the pressure inside the droplet will be always inclusive of outside pressure. The pressure inside the droplet will be always inclusive of the outside pressure. The pressure inside the droplet in excess of outside pressure. So the outside pressure is nothing but atmospheric pressure. For example, atmospheric pressure is say 10. So outside inside pressure, which is inclusive of that too, outside pressure. Now coming to the hollow bubble case. There are two popular case studies or examples, considering one is water droplet, the other one is hollow bubble. Similarly, the liquid jet. So let us take an example of hollow bubble. Hollow bubble, like a soap bubble, you can see there are two contact surfaces, one above the other, like a two coats. So in the case of the hollow bubble is nothing but just like a droplet. It has a sphere shape, and there are two surfaces, coatings. So hence the free liquid surface, actually free liquid surface in the droplet case or in the bubble case, it will be exactly equals to the circumference length, which is pi d in case of a droplet, which is 2 pi d in case of an hollow bubble, because there are two surfaces. And this multiplied by a surface tension, that is tensile force per unit length, denoted as sigma. Sigma into 2 pi d, that is one force which is acting here. The other force is actually pressure forces. When you observe this, there is, when you view from this angle, the projected area of this, they will be look like a circle. It has an area equals to pi d square by 4. Pi d square by 4 into P called pressure force. This is sigma. This arrow is indicating tensile force, that is denoted as sigma, also called surface tension, and multiplied by the unit length of the free water surface. This is exactly the free water surface. In the case of hollow bubble, that edge equals to twice the diameter. Twice the diameter, that is 2 pi d. In the case of the droplet, it is pi d. Why it is 2 pi d in case of an bubble? There are two contact surfaces, and each length will be equals to pi d, thereby it is 2 pi d. On equating these two forces, because they are equal and opposite. So by doing so, we get the pressure inside the droplet in excess outside, that is 8 sigma by d. It is exactly double the water droplet. Now coming to another example of surface tension in liquid jet. You can see this is specimen liquid jet which has a length equals to L, and liquid jet which has cross-sectionally circular, hence the d is the diameter. So now let us take the half of that. So when you look at this, when you carefully look at this, there is a surface tension, that this arrow indicates a tensile force due to surface tension. Sorry. Here, this edge is equal to length. There are two edges, hence the total length becomes 2L. Then sigma into 2L. When you view from this angle, this liquid jet will looks like a rectangle having the dimension. One side is L, the other side is D. That is L into D. So that is L into D into P, which becomes pressure force. Then sigma into, when this is called surface tension, it has a length equals to 2L. Then sigma into 2L becomes tensile force due to surface tension. By equating both, we will get this is a final equation. Friends, please remember, in the case of a surface tension, I have taken three examples, one for water droplet, the other one for hollow bubble, the one more for liquid jet. In these three cases, the formula for the pressure inside in excess of outside will be equals to 4 sigma by d, 8 sigma by d, 2 sigma by d respectively. The first one is for droplet, water droplet. Second one is for hollow bubble. This 2 sigma by d for liquid jet. Now, there is another property of the fluid. That another property of the fluid is called capillarity. In the capillarity, we have two cases. One called capillary raise, the other one called capillary depression. Well, even you look at this figure, when you observe carefully, here we have a liquid to which a small diameter glass tube is inserted, such a way that it is vertically inserted, such a way that the liquid is allowed to enter to this glass tube. The moment when the glass tube is held in the liquid like this, the water in the container will start entering the liquid and keeps rising in the glass tube. And it will rise above the general level of the liquid in this container. And that height will be called H. It keeps on rising and finally it comes to rest. Finally, it comes to rest. Then, when you view from this angle, you can see there is a free water surface here. We can also see the meniscus, and the free water surface, as we have discussed, it is always under tension. It is always under tension. So because of the meniscus, the tension is nothing but surface tension. That is denoted as sigma. And this, then tangential to the water inside the glass tube, it is written like this. Because of it has a meniscus. This is called surface tension. There is a small amount of inclination between the line of action of that tensile force with respect to the glass tube. That angle is called contact angle, denoted as theta. That value of the theta, which varies from liquid to liquid. And normally theta, unless otherwise specified, taken as 0 degree. In the case of water, the theta will be taken as 128 to 130 degree in the case of a liquid like mercury. And our aim is to find this height. This is called capillary rise, and the height by which the liquid rises in the glass tube, which depends on several factors. The factors are the surface tension of the liquid, the diameter of the glass tube, the density of the fluid. All these factors will influence this rise. And for that, we have a formula. The phenomenon of rise or fall of a liquid in a glass tube relative to the adjacent level of the liquid will be called as capillary rise or capillary fall. It is not all the time rise. It can also be a depression or fall. In the case of a liquid like mercury, it will have a fall. That is called capillary. Whether it is a rise or a fall, the formula for finding H is common abbreviation for both rise and fall. And this formula for sigma cos theta by rho GD, it is used to find the capillary fall or a capillary rise, where sigma is called surface tension and denoted as Newton per meter. Theta is nothing but the contact angle between the tube or glass tube and the liquid, where rho is the density of the liquid, d is the diameter of the glass tube, and that H depends on these three factors. And this is called capillary depression. Capillary depression, nothing but a heavy liquid like mercury, it will have a fall. Whether it is a rise or a fall, the formula will remain same. So friends, please remember this formula we use in the numerical problem while finding the fall or rise, capillary rise or a capillary fall. The same formula, with the only difference is the theta angle in the case of the fall will be slightly higher than that of rise. All other the letters meaning will remain same. Now coming to an example. The example of a numerical example of capillary rays. Look at the problem. The capillary rays in the glass tube is not to exceed zero point 0.2 mm of water. Determine the minimum size given that surface tension for water in contact with air is or has 0.075 Newton per meter. The dimension given, the surface tension is restricted to zero point 0.2 mm. The water is allowed to rise only this zero point 0.2 mm. And you are finding the diameter of the glass tube. The diameter of the glass tube by knowing the surface tension of the liquid. Here, the liquid is water, no doubt. So we use the, unless otherwise specified, the contact angle in the formula. There are many parameters. Rho is there, theta is there, density is there, diameter is there, h is there. We are actually finding the size, nothing but diameter of the glass tube. So what should be the diameter of the glass tube? If the liquid is water, when that is allowed to rise by 0.2 mm, the problem is very simple. Let us use the formula. Theta is not given. As I said, unless otherwise specified, the value of theta to be taken as 0 degree for water. In this formula, for sigma cos theta by rho GD, that H, that is called capillarity, that H value is given 0.2 into 10 power, since it is in mm to be converted to meter, and 4 into sigma. Sigma is also given 0.0. It is always in the unit called Newton per meter. We have to substitute all the values in the SI unit. 0.075 cos of 0 degree because of water. When the value of theta is given, you can use it. Or otherwise, for water only it is 0 degree. When it is water, for it will be 0 degree. In the case of mercury, it is 128 or 130 degree. Between 128 to 130 degree, any value you can use. So rho into G into D, where rho is 1000 because it is water, D you are finding, and when you substitute everything, you will get the diameter, which is 0.148 meter in the centimeter, 14.8. It is actually 14.8 centimeter dia glass tube, which is held in the container. Then the liquid rises by 0.2 mm, just 0.2 mm it will rise. Now coming to another example, you can look at this. A glass tube of 4 mm diameter is immersed in water of surface tension 0.0075 Newton per meter. The contact angle of water is 0 degree. It is exactly, it is only the exercise problem of 0 degree. What will be the capillary effect in millimeter? We are the answers are given. So you have to carefully work out. So in order to get the correct answer, it's immersed in water surface tension 0.075 Newton, the contact angle is 0 degree, you are finding the capillary effect, means capillary rise or capillary fall. Capillary rise formula is already known to you, 4 sigma cos theta by rho into G into D, where sigma is called surface tension, that value is given, 0.0075 is given, into cos of theta, theta is nothing but a contact angle that is given, that is 0 degree, and rho into G, the product rho into G becomes 9810, and diameter of the glass tube is also given 4 mm. Convert to meter and substitute here, and finally you will get the answer 0.76 millimeter, means that water will rise in the glass tube by this much amount. So now when you look at the options, the option B is the correct answer. So only thing is you have to carefully substitute. Sometimes you will substitute and without looking or without worrying about the unit, then you will get some other answer may correct, the unit may not be correct. You have to be very careful while substituting each parameter in the required unit. Now coming to the other topic, important topic in the field of fluid mechanics is the pressure. So what is basically pressure and what are the types of the pressure, how the same can be measured, and this is most important as far as the measuring the pressure of a liquid which is flowing in the pipe is, which is very important. Now basically pressure is nothing but a force by area, dF by dA. dF means an elemental force assumed to act normal to an elemental area. That ratio is called pressure or intensity of pressure. There is a formula, a popular law, Pascal law. Whenever the fluids are at rest, whenever the fluid are at rest, there is the pressure or the intensity of pressure which is going to be equal in all the direction, and that is equals to px, py, pz. All the three are equal. If you consider an elemental fluid and anything inside the liquid, any elemental portion of the liquid, if you take, which is going to be act are subjected by the several forces, and hence there are pressures each in each direction. And if you consider an elemental fluid, and that fluid is under the action of the pressure, and the pressure acting on an elemental fluid when the fluid is rest, which is going to be equal in all the direction. That's what the Pascal law statement is: Px, Py, and Pz. Now, there is another beautiful formula or an important formula in the field of fluid mechanics, which is called hydrostatic law. Many of the manometers are designed or working on this principle. P is equal to rho into G into H, which is nothing but the pressure intensity at any depth. If you have a column of a liquid, if you wish to find the pressure at any desired point from the free liquid surface, we have to use this formula. This formula is called the hydrostatic law. So rho into G, where H is at any desired depth, we can able to find the pressure of the intensity of pressure just by knowing the type of the liquid. It has a density. If you substitute the correspond, if you wish to find a pressure in a water at a depth equals to 2 meter from the free water surface, then substitute rho as 1000, H as 2 meter, you will get one value. That is going to be the pressure in water at 2 meter below the free water surface. Now coming to one numerical problem. That's why as I told several times, you have to be theoretically sound. Then only problems becomes easy. If you are really good at the theory, or if you understand the theory concept well, the problem's really going to be easy. Simply studying problem without understanding the background theory, then it's not going to be work. And please remember, you be good in the theory first. So we are going to calculate the pressure due to a column means height, of 0.3 meter of water if the density of water is 1000 kg per cubic meter. It is asked to find the pressure in water at a depth equals to 0.3 meter from the free water surface. As I said, there is a formula in order to find the pressure in any liquid column at any desired depth. For that, the formula is here: P equals rho into G into H. This is called hydrostatic law. Using this law, what you are going to find? You are finding the pressure intensity, where you are finding at a depth equals to 0.3 meter. In which liquid we are finding? In water. All are very clear. The depth is known, which is 0.3. The liquid is known, which is water. And when you substitute the rho of the water, 1000, G is a constant, 9.81, H is point, you will get the answer. That answer, 0.2943 Newton per meter square. It's like not cm square, which is because all are expressed in the unit called, this is kg per cubic meter. This is 9.81. When the product of this will have a resulting unit of Newton per cubic meter into 0.3, which is in meter. Hence, this unit will be 0.2943 Newton per meter square. Now coming to the types of the pressure. One should understand the pressure types. Pressures, we normally say gauge pressure, vacuum pressure, absolute pressure, atmospheric pressure. So we have to understand the correct meaning of this, because the gauge will measure the pressure, these pressures. So when the gauges are used, they measure the pressure using the two systems. When you look at the figure, in this figure, there are two horizontal layers. You can observe at the bottom you have one layer. Here also we have one layer. The bottom one is called absolute zero pressure or complete vacuum. The pressures are measured in using two references. The two references are one called complete vacuum or absolute zero. The other one called atmospheric pressure. So sometimes you measure the pressure using this as a reference. This as a reference. Please remember, we use this as a reference. Sometimes we use this as a reference. If the pressures are measured using atmospheric pressure as a reference, the pressures are only in two names. They are gauge pressure and vacuum pressure. When this system is used to measure the pressure, the two pressures are gauge and vacuum. Then what is gauge pressure? Gauge pressure one which is always more than the atmospheric pressure. Gauge pressure is one which is above the atmospheric pressure, whereas vacuum pressure is one which is below the atmospheric pressure. And what is actually absolute pressure? Whenever the pressures are measured using this system, this is called complete vacuum. Actually, atmospheric pressure, there is a pressure in the atmosphere. You forget about its magnitude. The scales are designed to measure from ER. So keeping this reference line as a zero, anything above
it will register here, that is called gauge. Anything below, it will register here, it is called. Hence, gauge pressure is always positive pressure, vacuum pressure is always negative pressure. Irrespective of the volume, value of the pressure in the atmosphere, the scale will have zero here. Anything above zero, we measure here. Anything below zero here, we measure here. So likewise, the gauge works. Similarly, in case of an absolute zero pressure system, so actually it is a real scale we use. The zero is here. Here is actually not a zero, but it is rounded to zero. The atmosphere pressure is rounded to zero. Anything above we measure as gauge. Anything below we measure as vacuum. In the case of absolute pressure, it is from the complete vacuum we are measuring the pressure, pressure which is more than the atmospheric value, which is less than the atmospheric value. That does it won't matter. Instead, its name becomes absolute pressure only. If the pressure at a point A, when you wish to measure from this system, it is up to here. It is up to here from 0 to ER. Similarly, if you wish to measure the pressure at a point B using this system, it is only ER. And these two pressures are commonly called by the name absolute pressure because of the system used is absolute zero system. When this system is used, there are two names always. They are gauge and vacuum pressure. Gauge pressure is also called positive pressure. Vacuum pressure, which is also called as negative pressure. Anything above atmospheric called gauge. Anything below atmospheric is called vacuum. Friends, please remember manometers. What is manometer? Manometer is one which measures pressure. In the manometer, there are several types. We have simple manometer, we have differential manometer, we have inclined manometer like this. Actually, in the simple manometer has the simplest form, which is called by the name piezometer. You are looking when you are looking at the figure, there is a right angle bent glass tube. Actually, this is a cross section of the pipe. The point A indicates the center of the pipe to which a right angle bent glass tube is fitted. This right angle bent glass tube is called piezometer. Its one end is always open to the atmosphere. The other end is fitted to the point in the pipe where you wish to measure the pressure. What will going to happen? There is a valve provision here. The moment when the valve is opened here, the liquid inside the pipe, it will rush to the glass tube and it will rise to some height. And finally, it comes to rest depending on the pressure inside the pipe. Let H is the height by which liquid rises. If that is known, then we can use the hydrostatic law, which is P equals to rho GH. Actually, the pressure intensity which is directly proportional to the height of the liquid in this tube. This is called piezometer. More the height, more will be the pressure. If there is a more pressure, it will have more rise. So depending on the pressure intensity inside the pipe, this is the simplest form of measuring the pressure using the simple manometer. The simplest form of simple manometer, which is called piezometer. You can see there is another simple manometer which is called U-tube manometer. Because of that glass tube which looks like a letter U, hence it is called U-tube manometer. When you see this, the same pressure we are measuring in the similar pipe using other type of the simple manometer which is called U-tube manometer. Carefully observe. So actually in the U-tube manometer there is a liquid called a reference liquid, also called manometer liquid. Normally we practice with mercury. This thick color block color indicate that a liquid in the manometer. The moment when you wish to measure the pressure in a pipe using this type of the manometer, the liquid, actually this end is open, the other end is connected to the point. So when the valve is open, the liquid enters the U-tube, enter the liquid, and it will try to push this liquid depending on the pressure inside. And when you observe carefully, the moment when the liquid acts on the liquid inside the manometer, the other side, some amount of rise can be seen. This can happen only when the pressure inside the pipe, which is more than the atmosphere pressure, because the other end of the manometer is open. Thereby, this free liquid surface inside the manometer in the right limb, which is always under the action of atmosphere pressure. But because of there is a liquid here that will going to act here, and there is a rise can be seen in the liquid, the low fall can be seen in the left limb in the manometer, which clearly indicate that the flowing liquid will have a pressure more than the atmospheric. Will have a pressure more than the atmospheric because of the rise of the heavy liquid. This will push the mercury, hence it can be rise can be seen. So this is going to be happen only in the case of pipes carrying pressure more than the atmospheric, nothing but gauge pressure. And to calculate the gauge pressure, we have this, and there is a dotted line. this dot, observe carefully. This is called datum line. This is called datum line. If you want to measure the pressure at any point, we will consider one pressure. Actually, uh, we can measure both gauge pressure and the vacuum pressure. Vacuum pressure is one whenever. Actually, this AA should have been ER. This AA should have been ER. This dotted line, we have to only we consider the, this is called datum line to be here. The year it is correct, but here it should be here. So now we can able to calculate the pressure inside using the hydrostatic law, that is PA plus this, the rho into G into this height only, that is equal to the pressure intensity on the same line AA on the right hand side. Right hand side we have only mercury, it has a corresponding height. This figure is only showing the H1 denoted, and this is sum of this, and this is not the correct way, and we have to take on the datum line exactly through this, so that we can find the liquid height here, we can find the mercury height here, and the pressure intensity will going to be equal on datum line, and thereby you can able to measure the pressure whether it is gauge or vacuum. The same phenomenon here also. In when the pressure is vacuum pressure is one which is lesser than the atmospheric value. Thereby, even though when the valve is open, the liquid enters, because the other end of the U tube, the mercury is under the action of atmospheric pressure, which is more than the pipe pressure in the inside the pipe. Thereby, mercury the right itself, which goes down, the corresponding rise can be seen in the other end. And finally, we take the datum line exactly through the mercury in the right limb, and pressure is always equal on AA line in the left side of the limb and the right hand side of the limb. And by doing so, we can find the pressure inside the pipe, whether it is a gauge or a vacuum. Now, coming to one simple example, a pipe contains an oil of specific gravity zero point 0.9. You just look at the problem. A differential manometer connected at the two ends, 2 points A and B, shows a difference in the mercury level as 15 centimeter. Calculate the difference of the pressure at the 2 points 133. These are the various answers. Calculate the pressure difference at the 2 points. Actually, in order to calculate, a pipe contains an oil of specific gravity zero point 0.9. A differential manometer connected to the 2 points A and B shows a difference of mercury level as, and now whenever the pipe is connected to a differential manometer is one which has two ends. The two ends of the differential manometer is connected at 2 points in the same pipe or in the two different pipes. But in this case, that those ends are connected to the point A and B of the same pipe, which carries a liquid which has a specific gravity of 0.9. And because of the pipe connected to the differential manometer, mercury starts showing difference, which is 15 centimeter. Friends, please remember, when differential manometer is used to the same a single pipe, this formula, it is the ready formula in order to calculate the difference in the pressure between the 2 points A and B in the same pipe. The formula goes like this: G into H, rho suffix G minus rho suffix 1. G is 9.81. H is the differential manometer reading, which is 0.15. The rho 1 and rho G and rho 1. Rho G is nothing but specific the density of the liquid inside the manometer. Inside the manometer, we have mercury, which is equal to 13,600. Rho 1 means the pipe, it is a density of the liquid inside the pipe, that is zero point 0.9 means 0.9 into 1000 becomes density, that is 900. Finally we have the answer 18,689 Newton per meter square, which is going to be the pressure difference between the 2 points A and B in the pipe carrying liquid of specific gravity 0.9. The answer is 18688 Newton per meter square, which is the answer B. Like this, so we can calculate the required parameter, whether it is a pressure, whether it is a difference in the pressure, or sometimes we can able to calculate the difference in the mercury or mercury difference between the two limbs. By giving some data, you will be asked to find some other data. So for that reason, you are supposed to be good. So you have to practice with some figure. You have to practice based on the data given. It is better to practice with a figure. You have to write a figure showing the cross section of the pipe and the manometer connected. And in the manometer, there are all the details are to be transferred. So then only it will become easy for you to calculate what is asked. And friends, and I will going to stop at this stage, and we wish to continue on 16th. We have the same continuation. The coming 16th, we have the continuations of the in which we are going to discuss the hydrostatics, the dynamics part, friction part, and the notches and VRs. Again, I am requesting you people, and you have to be very good. You have to be sound in the background theory for each, whether it is a measurement, whether it is hydrostatics, whether it is a dynamics. In the dynamics, we are going to use the Bernoulli's law, and that is the application of Bernoulli's law in the field of the fluid mechanics will be a vital. So, in order to design the Venturi meter, Horifice meter, which are used to find the flow measurement or the flow rate or the discharge. So, and I thank each and everyone for having participated in this, and wish you all the best for the coming gate examination. Okay, I thank you one and all.